I'd like to welcome now Bridget Buxton of the University of Rhode Island, who will give us a presentation titled Postcards from the Pladypos, Field Testing the First Generation of Cognitive Robots for Underwater Archaeology.
Okay, and I just have to do a quick switcheroo here. Get all this fancy Mac stuff out of the way and put a real computer on. Okay. Can I move this out of the way? Sorry. Thank you. So I realize that I'm the fifth talk in the morning, and that we're running more than 10 minutes behind schedule, and I'm the second person you have to listen to that has a funny voice. So I will try and keep all of that in mind.
Second person.
Don't sidetrack me on that issue, please. Okay. Show. All right. And the second Australian you're going to have to look at this morning. So I'd like to thank you very much to the organisers of the conference, Erin, Jody, Derek and Michael, for really, I think, creating a seminal moment in the development of this new ways of doing archaeology. And I'd also like to thank everybody who was a part of the Platypos project last summer, in particular the engineering team from the University of Zagreb Laboratory for Underwater Systems and Technology, the director of Israel Maritime Antiquities, Kobe Sharvit, and his team, my colleague John Hale at the University of Louisville, Julie Stark from ONR Global, Craig Howard from OceanGate Foundation, basically everyone on the t-shirt, everyone who supported us, dived with us, gave us money. I'm the one here reading this paper, but I think it will be very clear that the work I'm presenting is the work of many people and organisations. So I'm going to record just what's on the surface, and you don't need an excavation quality site map. For those of you who don't know, SLAM means simultaneous localisation and mapping, and it covers a variety of methods of determining where you are based on the data you've collected about where you've just been, which is actually a much easier problem to solve underwater than true navigation, because of course underwater you can't use GPS. Now there are some incredibly beautiful acoustic models of shipwrecks out there. I'm thinking in particular of this multi-beam work that was presented by Martin Dean from St Andrews at the BTS conference last year. This is achieved with very high-end equipment on budgets that are basically out of reach of your average archaeologist working in the Mediterranean. And again, our focus in this workshop is not just about digitising the past, it's also about mobilising it. And mobilising the kind of money, team and vehicles you'd need to get results like this is just on a completely different level from being able to grab your dive gear, slate, tape measure and laptop and be good to go at short notice. That's what being mobile is. So these examples of digital site recording may be great, and they may in fact be the only option for very large or very deep sites. But when you're talking about small, low relief, shallow water, in particular ancient ships and structures, and very limited budgets, and the need for mobility, you're going to have to come up with a different solution. So these are the kinds of challenges that for several years now I've been bringing up at a unique annual event that's held in Croatia called Breaking the Surface, which brings together some very talented designers in the field of marine robotics with the scientific end users who need their inventions. So this is the group of very smart people I've been harassing for many years to build me my dream site mapping robot, which is even sillier when you think about it for all the different oceanographic sciences and industries that these guys could be designing for. Why would they invest in building robots for the one oceanographic field that has absolutely no money? Well, I'll tell you why. It's because the stuff we do is awesome. Now, these photos of important discoveries were all taken very recently off the coast of Israel, and I'll come back to the significance of that in a moment. But first I want to introduce you to the team behind the technology. The Platypus robot we're about to see is the product of a European FP7 consortium called the CADDY project, the Cognitive Autonomous Diving Buddy, which was developed at the University of Zagreb, but with a lot of help from other international partners. Now, if you're interested in learning more about that project and the specifications of the vehicle itself, I strongly encourage you to check out the CADDY website and video. As you can imagine, the applications of this technology go far beyond archaeology. So what can the first CADDY prototype, the Platypus here, do for archaeology? Remember that impossible wish list of capabilities I described earlier: an affordable site mapping robot that can go anywhere, achieve sub 5 centimetre accuracy over vast submerged sites, with every point georeferenced to the same precision as on a land site, with automatic post-processing of all the data so that it all can be used in real-time speed of an excavation. I think you can understand my skepticism when I first saw this unusual and suggestively toilet seat-shaped device at the BTS workshop several years ago, and listened to my Croatian colleague and co-author Nikola Miskovic explain how this was going to be able to do pretty much everything I'd asked for. Well, last summer at the old Roman port of Caesarea in Israel, we had a chance to test out those claims. Now, this is a reconstruction of Caesarea built by King Herod of Judea in honor of his patron, the first Roman Emperor Augustus, that I think we're going to be hearing more about tonight. So this is the late 1st century BCE. Caesarea was built as a Greco-Roman city, with all of the trappings one would expect: theatres, hippodromes for chariot racing, pagan temples, and above all, a magnificent artificial harbour constructed in part from a special type of Roman hydraulic concrete that sits underwater to create really massive and impressive breakwater structures. Now, this harbour soon became the main port and capital of the Roman province of Judea, and at its height, Caesarea covered an urban area of nearly 1,000 acres. That's 5 times the size of Jerusalem. So Herod did everything on a grand scale, and for that reason, among others, the port of Caesarea has been very extensively studied for a long time. But while we know a great deal about specific areas that have been excavated and mapped by divers, and these reconstruction drawings seem very confident, don't they? In 50 years, there has never been an archaeological map made of Caesarea's entire harbour at the level of accuracy that I think is now the benchmark for underwater excavation. So this is all that remains of those giant Herodian breakwaters today, and past maps have literally, in many areas, have just been traced over the aerial photos like this. So that's why even this official site map is a little bit deceptive. There's a lot of missing and incorrect information here. So we would benefit in many ways from having a more detailed map of this entire site. There's no way we're going to handle that amount of data except on a purely digital platform. So how does the Platypus check out for this task? First of all, mobility, check. Weighs about 25 kilograms and can be launched from just about anywhere. Second requirement, robustness. As you can see in the bottom left image, we sent it out into a fairly moderate swell and it still collected good data. And this is always going to be your biggest limiting factor with a surface vehicle. But it's the trade-off you make for being able to use GPS. Meanwhile, you're recording your position relative to objects underwater using DVL and USBL, a Doppler velocity logger and an ultra-short baseline system, terms which probably mean nothing to most of us, but they are technologies that deal with a very, very difficult problem of underwater navigation. So as you can see, it was also easy to repair and modify the vehicle's instruments as needed by using a readily available adhesive technology. that we are all skilled in. Third requirement, easy to use and compatible with local resources. All you need are laptops. Now, the vehicle knows where to go when it has a mission programmed into it, but if by chance you want to take control of it, this vintage Atari video game joystick that we borrowed from Kobe's son, without his knowledge, is an option. And that's IAA's archaeologist draw planer at the controls there. Fourth requirement, speed of operations and post-processing time. Over a couple of days last summer, the Platypus collected more georeferenced measurements in the ancient port of Caesarea than teams of archaeologists have in the previous 50 years. But the best thing was that later that same day, even though there was still some processing to be done, Nicola here was able to give a presentation of the raw results obtained in the morning. So these are detailed bathymetric maps produced in real time. Now, as someone myself who is still waiting for maps and other data processing to be completed by engineers I worked with as far back as 2007, I can't stress enough how important this fast delivery factor is. So what is the vehicle actually doing on these inshore survey missions? It is recording the seafloor using a combination of acoustic and visual sensors. In clear, shallow sites like Caesarea, the Platypus can get quite nice resolution in about 8 to 10 metres of water. But its acoustic sensors are effective anywhere within normal scuba diving depths, which is what we want because everything we're interested in is in shallow water. And this is what the vehicle produced from a few minutes of hovering over the foundations of an old Roman pier that you just saw in that photo from Stotyam, south of Caesarea. So this is made up of many hundreds of images stitched together, and you can zoom in and see really fine detail. It's not shown on the slide, but you can. Importantly, you don't just have images, you also have the global location of those tiny details you're looking at. I know everyone working on land sites takes this for granted, but when you work underwater, knowing exactly where you are and staying on target is actually a very serious and difficult challenge. It's what differentiates the systems that cost a few $1,000s from the vehicles that cost a few $1 million. Now, the Platypus follows a path using dynamic positioning and DGPS to get a very precise fix on its location at all times. And if necessary, it can also use secondary transponders to greatly reduce the amount of error in the underwater targeting and navigation too. So that's point 5 taken care of, the need for precision. You can achieve the level of precision that you want, and the production of easily readable bathymetric data. These are the foundations of a couple of old Roman towers from Caesarea's inner harbour from the aerial photo that you just saw, plus some of the raw mosaic data. And these are the same results integrated into Google Earth. And eventually, of course, the photo mosaic can be stitched over the top of this data to give a 2.5D reconstruction. And if you want to get a real close look at what's going on with those towers, and more importantly, be able to pull up the measurements of what you're looking at, you can do that as well. Now, one of the brilliant features of the Platypus is that because it's designed for shallow water, which is where most of the shipwrecks are, it's not trying to reinvent the wheel, or in this case, the capabilities of a human diver. Because the Platypus has access to human divers, it has incorporated their functionality into its own tasks that would be expensive, difficult, or even impossible for an autonomous underwater vehicle. And the way the diver communicates with the Platypus and with the people on shore is through a perfectly ordinary tablet PC. So again, if you are greatly reducing the cost of a new technology, if you can maximize the use of assets that you already have, in this case your basic tablet and your cheap replaceable student divers, and so on. I didn't really mean that. I've never lost a diver yet. Always bring home the same number that I set out with. So the tablet is sealed in a specially designed underwater casing, and the divers, so what happens if it rains? Here, I've just answered your question. The divers can access most of its applications using a special touchscreen pen. So just this casing alone, I think, is an incredible leap forward, but that's not all that's going on here. What you can't see is that the Platypus, which is above, and the diver-based unit are actually communicating via a USBL and acoustic modem that maintains a low bandwidth link with the surface. That means the Platypus is always hovering over the diver, using its GPS to tell him where he is at all times and presenting him on the tablet with a map of his location via a custom GIS application. So the Platypus also allows people on the surface to have a fix on the diver's location and to send him email messages, which is really useful if you, say, live boating, trying to locate a sonar target in strong currents 4 to 5 kilometers from shore. You're far more effective and you're also far safer. So here is Kobi Sharvat of the Israel Antiquities Authority at Caesarea. And let's say he's just found something that's been exposed by a recent big storm, like, for example, if you've been watching the news, the 2,000 odd gold medieval coins that were found right here in Caesarea a few weeks ago. The first thing he's going to do after, the mild heart attack is he's going to use the tablet to take a photo of his discovery. Then he's going to tell the Platypus to mark the coordinates of the find spot straight onto the GIS. Then he's going to type on the tablet a brief label explaining the significance of the location he's just recorded, and he's going to archive it with the photo he just took under that map reference. Then he's going to write an email to the guys on shore with the laptop saying, "Hey guys, I think I just found a big pile of gold." Then maybe he's going to send in an order for pizza and email that Porsche dealership in Tel Aviv to expect him later in the afternoon. And then he's going to call his silly friends over, and together they're going to take the first underwater selfie on a tablet ever beamed directly from the seafloor via an autonomous surface robot directly to Facebook. You're seeing it here, folks. Which just goes to show, actually nothing, but let's imagine the next iteration of the Platypus, where Kobi's tank unit is actually also reporting his vital signs, his air consumption, and remotely coordinating a fleet of other intelligent underwater surface and aerial vehicles that are all helping him to do his job. This is not science fiction. The technology to do this exists right now. It's already at prototype phase. Let me be very clear about this. We desperately, desperately need this technology in Israel right now. I've been excavating with Kobi and the Israel Antiquities Authority here for the last few years at the submerged Hellenistic port of Archaeology. A few weeks ago, the big storm that blew through, it tore all of our square excavation caissons completely out of the ground. It literally did the next 3 years of excavation for us in one weekend. We're done now. So this is part of what that storm exposed, a massive Hellenistic quay, more than 50 metres long, and it was exposed during this event. So these once-in-a-century storms are now happening every single winter. I won't go into the reasons why the environment is changing, but what's happening is you have very delicate, very well-preserved archaeological sites that have been safely buried for centuries and in some cases millennia, and then you have them exposed suddenly after a big storm. So, for example, 16th century Venetian bronze Saker here, we found, raised that in 2013. We found an Ottoman warship in 2011, so well preserved that even the chicken bones from the last stew they ate on board were still in the pot. Now that same shipwreck was buried again less than a week later. It's a very violent process. So you have these short windows of time where it's absolutely imperative that you get out there and find and record as much as you possibly can before the sand returns and the site is lost. And the Platypus really answers that lead. And wrapping up now, It brings us to the most important question and the final requirement. How do I get access to this technology? What is it going to cost? Now, the actual components of the system are not that expensive to make. It's the intellectual property that went into the development that's the issue. But market value is not even the appropriate concept for this kind of robot, because it's hard to tell if it's even going to be a commercially viable thing. The tablet casing definitely, but the Platypus is obviously far more specialized. So one of the important ways I think that we can help mobilize the past is by forming research partnerships with the people building the technology and finding ways to make it worth their while to produce these custom robots for the projects that desperately need them. Sort of like a high-tech cottage industry, but run by NGOs. And I've even thought of a name for it. It's called Robots for the People. I even bought the domain name. And now I'm brainstorming with some friends about how we can mobilize more of these kinds of collaborations. The answer is actually very easy. We just need people to give us lots of money. But we're going back to finish Caesarea this July to finish that map, and very much welcome your comments, your non-engineering questions, and if you want to come by and visit us and dive with us this summer, you're most welcome to. Thank you very much.
Wow, amazing. Questions? Yeah, I'll just preface this by saying we're obviously running about 10 or 12 minutes late, and then there's a coffee at... Coffee break now, so we can just take a question. Yeah. Yeah, sounds great. I'll start by making kind of I don't know if it's a question or a comment, but I really like this in terms of the development of all these different talks this morning and finishing off here. It reminds me of just the kind of need to almost speak to other disciplines as well. Of course, underwater archaeology and archaeology are the same world, but I think some of the conversations we've had today, or this morning especially, remind me of just how unaware I am of other disciplines' anxieties, other disciplines' trials and tribulations with sort of trying to move toward, or trying or not to move towards these kind of digital platforms. And so if there are those in the room who know more about that, how do geologists handle this? How do geographers handle this? People hear me okay? Then I think that could be sort of very helpful for our discipline as well. Not just the different, whether you're doing archaeology in the Mediterranean or in South America or elsewhere. Other question?
Hi, I'm also a maritime archaeologist, but I work in Sweden. How does can this be applied to low light, poor visibility situations? I mean, more the visual thing where you take your photographs. Has it been thought of maybe using infrared or some sort of similar thing to work in very low light, low visibility situations? We work often quite in 10 centimetre visibility, so we can't see what you guys see.
Thank you. The question is about how do we use this technology in low light situations. I've worked in many places where you couldn't see your hand in front of your face, so I do get that. Visual measurements are distorted underwater. You have to use green lasers, and even they don't work in areas with a lot of particulates in the water, so the answer is acoustic measurement. Some of the images you see here, they look like photos. They're actually acoustic imaging of the seafloor. So that's the answer. We're using sound.
How tight are your points then in your point cloud between points?
I couldn't answer that question. If Nicola was here, he would be able to do that. My job is really just to nag them for finished results rather than to understand the process by which I get them.
It's really nice to have a model that you can actually measure, and when you come back from the field, that you can go back and take those measurements again and again. So
yes, as I hinted, I've had bad experiences before. So this was one of the key things. There must be a publishable data project before you let the engineers escape and go home. So this is very important to have that.
No, thank you, Bridget. I wanted to, I guess, sort of add something to what you said at the end that really hit home about the cost. Because we recently embarked in Cyprus on a 3D visualization project, along with most of everyone else that we meet. But what's interesting about it is that we worked with the team from we're working with the team from the University of Kentucky. And before we started, we were like, oh wow, a structured light scanner, and we had in our mind a grant where we needed to get I don't know, $50,000, $60,000, $70,000, and we talked to the Center for Visualization at Kentucky, and he gave us a parts list from Amazon that honestly was about $2,000. Now that's still a lot of money, but it's not $50,000. But then, those guys wrote all the programming. They designed the software. They did all the sort of background, all that intellectual property. And, the next step for us, though, was to talk to them about open source. Are they going to, because people keep asking us, well, can we do it? And the problem is that it's so specific to this Amazon-built structured light scanner that, for us to share it is becoming, hard. And so the next stages of our process really are going to be, can we build a toolkit? Literally a price list, a purchase list. This is what you have to buy. Here's how you put it together. Here are the things that don't work and do work, and then go here and get the software. But it's, I think it's difficult. I mean, because if you don't have that person that knows exactly how to put it together, from the technological side, you end up kind of floundering, I think. But anyway, it's a similar, it strikes me as very similar.
I know people need to get to their coffee, but if there's one comment of helpful advice, if you do get a chance to use new technology, or you buy some equipment, don't just get the equipment, get the guy who built it and knows it inside out. It's absolutely priceless to have those technical people on hand. Just don't think that you're going to buy it and learn how to use it. Have the problem solver there with you. It makes a huge difference.
Thank you, Bridget. There's a lot more to talk about, but also kind of coffee to be drunk, I think. If my sort of head pounding is anything to go by. So I'd like to thank Bridget and all the speakers. We can all thank them for this morning's great talks. And then there's coffee out that way.
Awesome. Thank you so much.
Thank you.
I'm, so